So today we're going to talk about geometric sequences, very similar to the arithmetic sequences that we talked about yesterday. One big difference is just the pattern that they increase by. So we're going to see some similar formulas and some similar strategies, but with a geometric sequence, it's just that the pattern is a different type of pattern. So we'll take a look at that. Now, a sequence or geometric sequence is still a pattern or an ordered list of numbers, and that pattern that increases by or decreases by is a pattern where we multiply to get to the next number. Instead of adding and subtracting, we're actually multiplying to get to the next number. That goes for if it's decreasing too. So if it is actually decreasing, for instance, if we see a pattern of numbers where it is decreasing and going down by, let's say, 2. So let's say I have a sequence of 12 and 6 and 3. All right, so we can say that this is decreasing by, most of you say that the pattern is that we're dividing by 2 to get to the next number, but really we want to keep that as a multiplying type pattern. So we would really say that it is being multiplied by 1 over 2, because remember, fractions represent division for us. So dividing by 2 and multiplying by 1/2 or 1 over 2 is how we would tell what it's multiplying by if this is a decreasing geometric function. So I have anything that I'm dividing by is going to be what's in the denominator, right? So let's take a look here at what we call that pattern. So here's another example. If I'm going from 3 to 9 to 27 to 81, so we can see this one's actually increasing. So it's easy to see that it is being multiplied by a whole number. And so it's being multiplied by 3 each time. So that pattern that we say it's multiplied by 3 is called a common ratio. Ratio meaning fraction. So common ratio, whatever it is that we're multiplying by, is not a common difference this time. It's called a common ratio, and therefore it has the variable r to denote. So let's look at how we tell it is a geometric sequence. If we're just given a list of numbers, yesterday with arithmetic sequences, we had to subtract to find the difference between them. Well, if we think it's increasing by a multiplication, we're not going to subtract, we're going to divide. So we're going to divide each term by its previous term. So I'm going to start with the second term, a sub 2, and I'm going to divide that by 4, right? So 8 divided by 4 gives me a ratio of 2. Right, so I want to make sure that that pattern is consistent before I say it is a geometric sequence. So 16 divided by 8 is also 2, and 32 divided by 16 is also 2. 64 divided by 32 is also 2. So because that does check out as a consistent pattern, then we say that 2 is our common ratio. And it is a geometric sequence. So if at any point I get a different ratio between two numbers, then I would say, no, it's not a geometric sequence because that pattern is not consistent. So we want to make sure we check throughout the entire sequence that it actually works. Let's talk about the recursive formula. Remember, recursive formula is going to be almost exact same as the recursive formula for arithmetic, because remember, recursive just tells us what the first term is, and the second piece of information, what's the pattern to get to the next number. So remember, the only difference between arithmetic and geometric is that arithmetic, we had a plus d here. We had adding some number. And then with geometric, we're not adding, we're multiplying. So we would just have that same notation, just multiplying by your common ratio. So remember, it has two pieces. Two pieces of information. I have to know where it starts. Give me my first term. I put a little semicolon in between just to give some space. And then a sub n equals a sub n minus 1. None of that changes. Whether it's geometric or arithmetic, we still write this part the same way. The only thing that's different is we say multiplied by whatever your pattern is. A pattern. So I have a sequence that goes from 6 to 24 to 96 to 384, and I want to make sure that that pattern is consistent. So I would divide 24 by 6 and 96 by 24 and 384 by 96, and I find that there is a pattern of multiplying by 4. So that common ratio is 4. And therefore, it's super easy. I'm just going to write my two pieces of information because I already know what my first term is. So a sub 1 equals 6 because I know. I'm going to write a little semicolon to separate my second piece of information. A sub n equals a sub n minus 1. Remember, that doesn't change. It's just notation. We're not going to plug numbers in there. And minus 1. And then times 4. We can also take this 4, and because I'm multiplying it by a variable over here, I can put the 4 or write the 4 first. So I could write this as a sub n equals 4 times a sub n minus 1. Right, and that's just writing in normal algebraic notation with the coefficient in front. Sorry about my awful writing. Explicit formula for finding the geometric sequence is a little simpler than the arithmetic formula because it really looks just like the recursive. I'm going to be multiplying a sub 1, my first term, times my common ratio. Now that common ratio is going to have an exponent. So your geometric sequence, your explicit form, is an exponential function. But I only need two pieces of information. I need first term and common ratio, or my pattern, to put that together. All right, so let's take a look at how I would write that for this formula. So I only need those two pieces of information. So I know that my first term is 6. I know that my common ratio is 4. And now I'm just going to write it. All right, and remember, this is the explicit form that allows us to get to any term we need to in the sequence. And so after we write it, we're going to find the 7th term in this sequence. All right, so a sub n is going to equal a sub 1, which is 6, times, let me use parentheses, r, which is 4, to the n minus 1. That's it. It is that simple. Those of you that are cheating on your homework, I don't know why. It's a super basic concept. You could get this very easy. Remember, we're on like day 2 of our new unit, and day 1 and 2 are always the easy stuff, right? Okay, so we're going to find a sub 7. A sub 7 equals, all I'm going to do is I'm going to substitute a 7 in here. So I have 6 times 4 to the 7 minus 1. Of course, if you're cheating on your homework, you're probably not watching this video, so I guess I'm just preaching to the choir at this point. So 7 minus 1 equals, all right, now I have to make sure, order of operations, I account for this exponent first. So 6 times 4 to the 6th power. Parentheses. All right, and then the 6th power. So I do need a calculator for that. So my 4 to the 6th power is 4,096. That's a 6, y'all. All right. All right, so 6 times 4,096. So if I were to continue this pattern and move it all the way out to the 7th term, that would get me to 24,000. So this is an exponential function, which we know grows very quickly. So even though we've got 4 of the terms here, by the time we get to 3 terms later, we're already at 24,576. So it grows very quickly. All right, I'm going to talk about one more topic, and that is how to find the geometric sequence pattern if you are given 2 terms in the sequence, and sometimes those terms aren't consecutive. So what I'll do here is usually I'll just draw spaces to represent. So I have my first, second, third, fourth, fifth, and sixth numbers, and I know that 512 goes in the sixth term, and I know that 2 is in the second term. So we have to think that we're multiplying by the same number to get to this number. So what I need to do to figure out the pattern between them is I first got to find out what is the ratio between these two numbers. So I'm going to go ahead and divide. So I'm going to start by saying 512, and I'm going to divide it by 2. All right. So the distance between those numbers, I can do this work already, is 256. All right. So 256. All right, so 256 is what I'm actually multiplying by to get all the way here. So we have to think. I'm multiplying by the same number each time to get to 256. So that number that I'm multiplying by is really multiplying by itself, right? It's being raised to some exponent. Well, how many times is it multiplying by itself? Well, to get from here to here, I've got 4 spaces, right? So I'm going 1, 2, 3, 4. I'm multiplying some number by itself 4 times in order to get a difference of 256. So that is essentially saying, right, there's some number that is being raised to the 4th power that's going to give me 256. So if I can figure out what that number is, what number is it that is raised to the 4th power, then that is my R, my common ratio. All right, so let's see if I can take the 4th root of 256. It tells me 4. So 4 is the number that I'm multiplying by itself 4 times to get 256. So if I multiply 2 times 4, it gives me 8. 8 times 4 is 32, and so on. If I keep that pattern, that's going to get me complete the pattern and get me to 512. So I know that my R is 4. The other piece of information I need to know is my first term. So if I need to multiply by 4 to get to the next term, then I would divide by 4 to get to this first term. So if I divide 2 by 4, that's going to give me a reduced fraction of 1/2. So now I know my first term and I know my R. So I'm ready to write my explicit form. So A sub n equals first term, which is 1/2, times R, which is 4, to the n minus 1. I tried to draw a big square, y'all. This thing doesn't like me. All right, so I'm going to give up on that, and there's my answer. So I'm also going to give up on doing this problem because this video is getting too long, and my writing is really difficult to do. All right. I know that's a little hard to understand without me working out, but please ask questions if you need to, guys. Homework is on Canvas.